Welcome to lecture 2 of module 1. In the last lecture we have discussed on various mechanisms of heat transport.
Now we will discuss a little bit on conduction. We will go in deeper into conduction. First, what we will try to do is that we will find out a general heat conduction equation. General heat conduction equation, and this heat conduction equation will be developed based on first principles, basic energy balance equations. In fact, we will see that general heat conduction equation both for all Cartesian coordinate, cylindrical coordinate and spherical coordinate system. What we understand by the general heat conduction equation is that it takes care of a situation, the equation which will be developed that takes care of the situation when you can have unsteady state heat conduction, when you can have temperature variation with time, temperature variation with space, and there is a possibility of heat generation within the body through which the conduction phenomena we are discussing. So, now to start with, we will take the volume elements for different cases. To start with, we will take the volume element for Cartesian coordinate system. Let us draw a volume element for the Cartesian coordinate system. So, let us draw the axis first. So, this is your say x, this is y and this is say z, and say this is the volume element, and so this is dy, this is dz, and this is dx. And what is happening is like so in this phase it is q dot y, and this phase it is q dot y plus dy. Okay. Similarly, say this phase, if this is q dot z, this phase it is q dot z plus dz. So, what is this? Q dot y means that heat is rate of heat transport at plane y, and q dot y plus dy means rate of heat transfer at plane y plus dy in the right hand side. Q dot z means rate of heat transfer at the bottom plane, and z plus dz means rate of heat transfer at the top plane. Similarly, you can have q dot x, and that is the x direction, and you can have q dot x plus dx. So, these are the rate of heat transfers. At the same time, we can have say heat generation within this volume element, and we will say that q dot chain is the rate of heat generation per unit volume. So, into the volume, what is the volume of this element? The volume of this differential element is dx, dy and dz. The volume of the differential element is dx dy dz, and this is q dot gen is the volume of the differential element. Rate q dot chain into dx dy dz is the rate of heat generation in the differential element, and we will assume that rate of heat generation is uniform throughout this volume element. Okay. Now, based on the first principles, we will do the analysis. According to the first principles or the energy balance, we have to do according to the energy balance, we will say that rate of energy conducted in plus rate of energy heat energy generated within the volume element this should be equal to rate of energy conducted out mind it that we are just taking care of only conduction mode of heat transfer, there is no other thing is happening in this volume element. So, rate of energy conducted out plus rate of change in internal energy or rate of energy accumulation within the volume element. Energy means we are considering again that in all the cases we should say the rate of heat energy, and rate of heat energy accumulation within the volume element. Okay. This also can be called as rate of change of internal energy of the volume element. Now, let us tell that term 1 is the rate of heat energy conducted in as term 1, then rate of heat energy generated within the volume element as term 2, rate of heat energy conducted out as term 3, and rate of heat energy accumulation within the volume element as term 4. So, then we have 1 plus 2 is equal to 3 plus 4. Now, we will find out what is 1, what is 2, what is 3 and what is 4. Now, term 1 implies what? Term 1 says that it is q dot x plus q dot y plus q dot z. All the rate of heat transfer from heat entered, not transferred, it is entering into the volume element q dot x, q dot y and q dot z. Then what is this term 2? Term 2 says rate of heat generated within the volume element. So, we have told q dot, it is already we have written that q dot generated into dx, dy, dz. Now, what is term 3? Term 3 implies it is the heat energy conducted out, that means q dot x plus dx plus q dot y plus dy plus q dot z plus dz. And then what is term 4? Term 4 is that rate of energy change, rate of internal energy change or rate of energy accumulation within the volume element. So, how is it? So, what is the energy within the volume element? If rho is the density of the volume element and dx, dy, dz is the volume of the volume element. So, rho into dx, dy, dz is the mass into Cp is the specific heat of the volume element into mCp into dt. So, it is you can say del T by del T. I am writing del T by del T because we will see that temperature will try to see that is a function of time as well as coordinates. In this case, it is a Cartesian coordinate system. So, in this case the coordinates are x, y, z. So, it is a we are finding out the general heat conduction equation in Cartesian coordinate system. Okay. Now, so these are the 4 terms. Now, we will see each and every terms, even for finer details we will go. For term 1, we know that q dot x is nothing but minus k into area. Area here in the case is dy dz is the area, dy dz is the area minus K A, this is as per the Fourier's law of heat conduction, into del T by del x. Similarly, q dot y is minus K into the area would be dx dz, okay, into del T by del y, and q dot z is minus k into dx dy into del T by del z. Now, if we see that between term 1 and 3, so if we write 1 minus 3, that means it is equal to q dot, I am sorry, it is it will be q dot x minus q dot x plus dx plus q dot y minus q dot y plus dy plus q dot z minus q dot z plus dz. Now, if we apply Taylor series expansion, we will find between these it is that this is del x of q dot x into dx plus del y of q dot y into dy plus del z of q dot z into dz. Now, we know what is q x, what is q y, what is q z. So, if we put over here, then what we will get is, we will get as del x of minus k dy dz del t by del x into dx plus del y of minus k into dx dz del t by del y into dy plus del z of minus k dx dy the del t by del z into dz. Now, we will assume that, I am sorry, one thing I should say in this in this term, this will be minus of this will be minus of this, and this will be minus of this. So, this is then becoming minus of this plus minus of this plus minus of this. Now, we will assume that K, that the material is isotropic. That means K is independent of position, material is isotropic, K is independent of position, and in that case we can take K out of the differential. So, in that case what we will write is that K dx dy dz into del square t by del x square plus K into dx dy dz into del square t by del y square plus K into dx dy dz into del square t by del z square. That means, we can write it as K dx dy dz into del square t by del x square plus del square t by del y square plus del square t by del z square, and this is equal to 1 term 1 minus term 3. So, if we see that previously it was 1 plus 2 is equal to 3 plus 4. So, 1 minus 3 is equal to plus 2. Now, if I write 1 minus 3 plus 2 is equal to 4 from the previous case. So, 1 minus 3 we have got as K into dx dy dz into del square t by del x square plus del square t by del y square plus del square t by del z square. So, this is between the 1 minus 3, then plus 2 we have already seen what is 2. If we see that 2 is q dot gen dx dy dz, it is q dot gen into dx dy dz, okay? And then that is equal to 4. What is 4? Already we have seen 4 is rho Cp dx dy dz into del t by del t. Rho Cp dx dy dz into del t by del t. So, now we can do, if we divide all sides by dx dy dz, that the volume element, then what we get is k into del square t by del x square plus del square t by del y square plus del square t by del z square plus q dot gen by q dot gen is equal to rho Cp into del t by del t, or now this term is called it is grad square t or del square t, which is called differential operator del. So, grad square t, grad square is equal to, I will tell grad square t is equal to q dot, I am sorry, grad square t plus q dot gen by k equals to 1 by alpha del t by, this is t, del t. Now, you see this equation here, this is the vectorial form of a general heat conduction equation. It is also called as Fourier field equation. Fourier field equation in rectangular coordinate. This is also sometimes called as Fourier's second law of heat conduction. So, like that the different names are given, but what we find here is this dat square is that, or sometimes called del square, it is basically del square by del x square plus del square, it is a grad operator, del square operator, y square plus del square by del z square. Now, it is a generalized form of the heat conduction equation for rectangular coordinate system, and where we can see that grad square t term says that temperature distribution within the coordinate for which is varying with x, y and z, temperature distribution within the volume element, q dot by gen q dot gen by k, that is that heat generation terminology, and alpha is k by rho C p. This is also called thermal diffusivity. This has got an unit of meter square per second in SI unit. So, this thermal diffusivity is similar to momentum diffusivity in fluid mechanics. They have got similar kind of physical significances like mu by rho nu. This is momentum diffusivity that is used in fluid mechanics, and small d, capital D, this is called diffusivity, molecular diffusivity you can say. That is used in mass transfer. So, for heat transfer operation, this is the thermal diffusivity, which is k by rho Cpt. K is the thermal conductivity, rho is the density, and Cp is the heat capacity. And in momentum diffusivity, that nu is mu by rho. It is used for mu is equal to viscosity, rho is the density of the fluid, and this momentum diffusivity is applicable for fluid mechanics. The momentum transport is involved, and D is the molecular diffusivity, which is applicable particularly for mass transport when the mass transfer is involved. Now, so grad square T plus q dot gen by k into equal to 1 by alpha del T by del T. This is a general conduction equation, which is also called as Fourier equation in rectangular coordinate system. Now, we will similar way we will try to see that heat conduction equation for cylindrical coordinate system. So, let us try to draw a figure again for the cylindrical coordinate system. If we say x, this is y and this is z, and say yes, this is phi, this is say d phi, okay, and say this is r, and this part is dr. And this part is dz. Okay. So, here exactly in the similar way, if we go for the you see here there are three things, this is dz, this is dr, and another part is r d phi. So, if we go in the similar way, the volume element is, so we have again the 4 terminologies, term 1 plus 2 as we have seen previously equals to 3 plus 4, and again here 1 equals to q dot r plus q dot phi plus q dot z. So, r phi z is the coordinate, that is the cylindrical coordinate. Okay. And exactly in the similar way, 3 is q dot r plus dr plus q dot phi plus d phi plus q dot z plus dz, and 2 is, what is that? 2 is the generation term. So, we will say that this is q dot generation into the volume element, and the volume element will be dr dz and r d phi. R d phi is the small section, that is this one, r d phi, this one is r d phi into dr into dz. So, that becomes the volume of the volume element. Okay. Now, and your 4 term is again that is the accumulation term or the change of internal energy, rate of change of internal energy. In the 4th term, it should be that rho Cp into dr dz into r d phi into del t by del t. Again here what we are doing is, we are assuming that t is not an assumption, we are calculating that only, that t as a function of coordinates as well as time. So, now again exactly in the similar way, 1 minus 3 as we have done, that implies minus del q dot r by del r into dr plus minus del q dot phi by del phi into d phi plus minus del q dot z by del z into dz. Okay. Now, we have to find out what is this q dot r, q dot phi and q dot z. So, q dot r equals to, again using Fourier first law or the Fourier law from the phenomenological law. From there what we see is that q dot r is equal to minus k into area. In case of r, it will be r d phi into dz into del t by del r, and I am sorry, del t by del r. Then q dot phi will be minus k dr dz. This is the area, thermal conductivity into area into del t by r del phi. Okay. And q dot z equals to minus k into r d phi into d r into del t by del z. Now, if we put all the 3 values in the previous case, what we are going to get is, we will be getting k into r into del r of k into r d phi dz del t by del r into dr plus, so this is 1 minus 3 equals to plus del phi into k into dr dz into del t by r del phi, okay, into d phi plus del z into k r d phi dr into del t by del z dz. Now, we again the similar thing that we will assume that k is independent of the volume element or coordinates. So, under that situation we can take the k out, but one thing we will say you, because r is there, r cannot be taken out. So, what we will write is k, this is equal to k d phi dz into dr, this dr is taken into del r of r del t by del r. Then we get plus k into d phi dz dr into, we will get del phi of del t by r del phi plus k into d phi dr dz into r. So, del z of del t by del z. So, we can write it like this, k into, if I take one r also here, r d phi dz dr, then we can write it like this, 1 by r del r of, because we have taken one r here, into r del t by del r plus, so we have taken one r here. So, it should be 1 by r square then into del square t by del phi square plus del square t by del z square. So, this happens to be the 1 minus 3 term. Now, if we write 1 minus 3 plus 2 equals to 4, as we have written in the previous case, then we will get, again if we write that k r d phi dz dr, k r d phi dz dr into 1 by r del r of 1 by r del r of r del t by del r plus 1 by r square del square t by del phi square plus del square t by del z square. If you see 1 by r square del square t by del phi square, this is this, plus the second term is, we have seen q dot gen this, it is q dot generation into r d phi dz dr, okay, that will be equal to 4 term will be equal to again r d phi dz dr into rho C p into del t by del t. Thus, if you divide by the volume element r d phi dz dr as we have done previous case, then what are you going to get is that 1 by r del r of r del t by del r plus 1 by r square del square t by del phi square plus del square t by del z square okay, and that is becoming equal to q dot generation by k plus 1 by alpha, sorry, this is plus and this is equal to 1 by alpha, you have got del t by del t. So, here also we can write or we can write that grad square t plus, as we have done previous cases, q gen by k is equal to 1 by alpha del t by del t. Here also this is the same thing, similar form we could find out again in case of cylindrical coordinate system, and alpha is again the thermal conductivity, which is k by rho Cp, and grad square t, this is the grad square is the operator, this is a differential operator in case of cylindrical coordinate system, and we can understand that grad square is 1 by r del r of r del r plus 1 by r square del phi, del square by del phi square plus del square by del z square. So, this way we can find out that general conduction equation in cylindrical coordinate system also. Now, exactly similar thing we can repeat for spherical coordinate. If we do it for spherical coordinate, system, let us draw this first. Okay. So, this is y, this is x and this is z, and you have so this is d theta and say this is theta, okay, and here we can say this is d phi, this is phi. Okay. So, what are the you have this part is, you can understand this is your r, this part is dr and this part is r d theta and this part is say r sin theta and d phi. This is what. So, under this situation, now again the same thing, same concept will apply. What we will get is that 1 minus 3 plus 2 plus equal to 4, the same terminologies will apply, and we have that equation again, that minus del r of q dot r into dr plus minus del theta q theta into d theta plus minus del phi q dot phi into d phi. This is nothing but 1 minus 3 equals to this. Now, again that we have to put that what is q r dot, what is q theta dot and what is q phi dot. Q dot r equals to minus k into r d theta r sin theta d phi, r d theta r sin theta, this is the area, into del t by del r, and then q dot theta equals to minus k into area is dr into r sin theta d phi into del t by r del theta, and q dot phi is equal to again minus k into dr into, here you will be getting r d theta into del t by r sin theta del phi. Okay. Now, once you put these things here, then club all this together. If we put all this here, then we will get all these expressions in this previous equation, and then what is 2, that is generation term is, it is equal to q dot generation into dr r d theta into r sin theta d phi. So, this is the volume element, this is the volume element into this. So, it is the total entropy generation, and 4 total energy generation, and here 4 term is that change in rate of change of internal energy or rate of change of rate of accumulation, that is again the total volume is dr r d theta r sin theta d phi into rho into Cp into del t by del t. Now, exactly in the similar way, if we do the if we substitute all the things there and do the derivations, we will land up with this equation, that 1 by r square del r of r square del t by del r plus 1 by r square sin theta del theta of sin theta into del t by del theta plus 1 by r square sin square theta into del square t by del phi square plus q dot gen by k, okay, equals to 1 by alpha del t by del t. We will come down to same this kind of expressions, and this can be written as again the gat square t plus q dot gen by k is equal to 1 by alpha del t by del t. So, we can understand that for all the cases, even for Cartesian coordinate or cylindrical coordinate or spherical coordinate, in all the cases we can develop this into this kind of equation, and heat conduction equation we can develop, and from there we can see that this general heat conduction equation, or what is that Fourier field equation, this equation can have different assumptions, or applying different constants into this equation, we can simplify this into some different forms. For example, if we say that it is a steady state operation, if we say that it is a steady state process, steady state heat transfer. When we say steady state heat transfer, that means we are telling about that temperature should not change, or the process parameters should not change with time. So, under that situation, what we can say that gat square t plus q dot gen by k is equal to 0. So, this is an equation. This is an equation which is called Poisson's equation. This equation is called Poisson's equation, and when there is no heat generation, when there is no heat generation, that means q dot generation equal to 0, when then we have 0 and at steady state, and at steady state grad square T equals to 0. This is called Laplace equation. In fact, these are the two equations which are the simplified form of the heat transfer situations. In practice, actually, I have told that grad square T, this equation is the general conduction equation, but grad square T plus is equal to, when we write the equation like this, grad square T equal to 1 by alpha del T by del T, then, or when we write that del T by del T is equal to alpha grad square T, actually this equation is called Fourier field equation, not the earlier one. So, this equation is the generalized equation, generalized conduction equation, which is applicable to all the coordinate system, but when we say that no heat generation term, then del T by del T is equal to alpha grad square T. This is called Fourier field equation. When there is heat generation term is there, but there is, it is at steady state situation, then it is called Poisson's equation, and when no heat generation and steady state, then grad square T equal to 0, this is called Laplace equation. Actually, if we see, initially I have told this equation, we should say that this whole equation, this equation without this term, when this is not there, when this is equal to 0, then this whole equation is called Fourier equation in rectangular coordinate, or Fourier second law of heat conduction. But in general, this whole equation is called the general heat conduction equation, which we have seen for all the cases, like in case of cylindrical case coordinates also, we find this is the general heat conduction equation, and in spherical coordinate system also we find the general heat conduction equation. Okay. But the Fourier field equation is this equation when the generation rate is 0, there is no heat generation within the body. Okay. So, this is the way. So, now what we can say that whenever we start with any coordinate system for learning the conduction equation, what we understand is that we have to start with a very, we can start with a very basic equation, that is that generalized conduction equation, and then depending upon the constants, depending upon the applications, we can reduce this to simpler forms and apply for our problems. One thing I should say here, that Laplace or the grad del term or the grad square term here is 1 by r square del r of r square del r plus 1 by r square sin theta del theta of sin theta del theta, then plus 1 by r square sin square theta del square by del phi square. So, this is called, this is the Laplace operator del square in case of spherical coordinate system. Okay. Now, we will try to see discuss some small problems related to this. But the first thing what we will say is that very small thing, that what are the assumptions behind this general conduction equation, whatever we have developed. What are the assumptions, main assumptions or the major assumptions behind the derivation of the general heat conduction equation. Yes. So, we can understand that this is basically two things we have assumed. First thing is that K, thermal conductivity, this thermal conductivity has been assumed to be independent of the coordinates as well as temperature. So, K is independent, particularly independent of coordinate that we have assumed. And another important assumption is that we have assumed that heat generation is uniform within the volume element. Okay. Now, we will see some other problems. Let us suppose that we have this equation of general conduction equation, the general form we have found out. Now, if we say that the reduce the equation, so what is the general form of equation we have found? We have found the general form equation, the GAT square T plus Q dot chain by K is equal to 1 by alpha del T by del T. Now, the question is, now what happens to this equation in Cartesian one dimensional sorry one dimensional heat conduction situation plane wall at steady state. So, what happens to one dimensional heat conduction equation in a plane wall at steady state? How this equation should be reduced? So, what we will do that? So, let us consider just any situation, say a plane wall, and this is the station one side 1 and this is the side 2, and let us consider this in the x direction. So, we are telling one dimensional, that means the heat is conducted along x direction. So, then what is happening is one dimensional heat conduction situation in plane wall at steady state without heat generation. So, what happens? Now, if we see that our basic equation is this, GAT square T plus Q dot J by K is equal to 1 by alpha del T by del T. Now, what we will do is that it is told that it is steady state. So, once it is steady state, so this term goes 0 because it is steady state. And then there is no heat generation. So, this term is 0 because no heat generation, correct. Then what is left is, so this is, we can say that GAT square T equal to 0. Now, the question is that if we remember what is this GAT square term, then we will find out that del square T by del x square plus del square T by del y square plus del square T by del z square equal to 0. Now, we are telling that it is a one dimensional heat conduction, that means there is no heat transport along y and z direction, that means there is no gradient along y and z direction. So, if there is no gradient, because we know that if there is a heat transfer has to be there in y direction, then q dot y has to be linked to it is equal to minus some k, okay, into del t by del y. So, this part is, if there is no conduction, then this has to be 0, and if this is 0, so del square T by del y square has to be 0. So, in along y direction there is nothing. At the same time, del square T by del z square equals to 0. So, that the gradient of temperature is 0. So, their second order derivatives are also getting 0. So, for one dimensional heat conduction, these two are 0. So, that means what is happening is, then we are reducing this problem into this kind of situation, where we can say that del t by del x, del square t by del x square equal to 0, and this implies if we do the integration twice, we will find that t is equal to c 1 x plus c 2, where c 1 and c 2 are the integration constants. Okay. Now, this c 1 and c 2, that means what we can say, from the basic equation under these conditions being applied, we are able to get the temperature profile. Okay. We are able to get the temperature profile within this, and we can see that the temperature profile is a linear profile. So, T is equal to C 1 x plus C 2, it is a linear temperature profile that we are able to get. Okay. And we can find out the values of C 1 and C 2 based on the conditions at, if we put conditions at station 1 and station 2, putting conditions at stations 1 and stations 2, we can get C 1 and C 2 values. Okay. So, this is the way we can simplify, starting from the conduction equation. For any problem given to us, we can simplify these for our understanding, for getting a temperature profile. Exactly the similar situation can be applied, similar things can be applied for cylindrical coordinate system, similar thing can be applied for Cartesian coordinate system. This can be applied, and in due course of time we will see that how these equations can be applied, and to get some pictures, some understanding of the heat transfer phenomena that is taking place by conduction mode in a Cartesian coordinate system, in a rectangular coordinate system, or in a spherical in a cylindrical coordinate system, or in a spherical coordinate system. So, just now we will stop here with this.